And the first question we want to talk about today is why are both charges attracted to my hand, which presumably is neutral, right? Now, someone said earlier, inducing a dipole. So we need to think about what that means. And we have to go back to what matter is made up of. And in my hand, we said matter, it's made up of atoms. And so here's a cartoony picture of an atom. Here's the nucleus, which is positively charged. And then surrounding a nucleus are the electrons. And quantum mechanics tells us that we can't really know precisely where the electron is and how fast it's moving, what direction it's moving at any given time. So there's sort of a cloud of probability. There's some region surrounding the nucleus where it's very likely to find the electrons at any given time. Okay, so this is sometimes called the Electron Cloud. Okay, and ordinary atoms have the same number of protons and the same number of electrons, and the electron cloud is essentially centered around the nucleus. Okay, let's say I bring a positively charged object, like a point charge, like a bare proton or something like that, near this neutral atom. What's it going to do? How's it going to affect the atom? The electrons will be drawn closer to it. The electrons will be drawn closer to it, right? The electrons, how's the mass of an electron compared to the mass of the nucleus? It's very, very small, right? So if anything's going to move here, it's going to be the electrons. The nucleus is essentially very massive, okay? So we can treat the nucleus as essentially staying still. The electrons are very light. They're free to float around. And this positive charge is going to attract the electrons. So the electron cloud actually shifts a little bit due to the attraction. And so this is kind of an exaggerated picture. The real shift might be only a fraction of a width of a nucleus, but it's big enough to notice. And if you have now a greater distribution of negative charge on this side and a concentration of positive charge on the other, that's an induced dipole. This is what we call an induced dipole. Okay. So a permanent dipole, which we talked about last time, permanent dipoles are dipoles all the time, and there are certain molecules that are just dipoles all the time, no matter what you bring near them. Okay, water is a permanent dipole, hydrogen chloride. But ordinary matter you can actually induce or create a dipole by bringing another charged object nearby, and that dipole will only be around for as long as the charged matter is around. Take the proton away, there's no more electrical attraction. The electron cloud would shift back to the equilibrium position. Okay, so this is an induced dipole. Diagrammatically, we're going to represent an induced dipole by just drawing a little oval with one end negative, the other end positive. Okay, so this is a convention that's used in the textbook to show a molecule or an atom that has been turned into an induced dipole by the presence of an electric interaction. Okay, so let's think about, we'll ask a couple questions here. So a positive point charge causes a neutral molecule to polarize as we just showed. Okay, what is the direction of the electric field at the location of the point charge due to the induced dipole? Okay, so now we know this is an induced dipole. We know about the directions of electric fields due to dipoles. think about the direction of the electric field at this location due to the dipole. Okay, so just about all of us say that the direction of the electric field due to the dipole at the positive charge location is to the right, okay? Don't even have to think about the positive charge. Once you have the dipole polarizing this way, the field is pointing towards the negative end of the dipole. Okay, so direction number 3. So, if we know the direction of the field, what's the direction of the electric force? This should take 30 seconds. It's got to be direction 3. Okay, it's got to be direction 3. If the electric field is pointing in direction 3 and you place a positive charge there, the charge is positive, Q times E gives you a force vector that's in the same direction as the electric field. Okay, so you get an attraction, right? So this is just showing that a positive charge creates an induced dipole. The dipole, or we say the polarization, is such a way that you get a attraction towards an attraction on the positive point charge. Well, what happened if we brought a negative point charge near a neutral molecule? How is it going to polarize? Which of those pictures would show the correct polarization? This term polarization is just another way of saying a separation of charge, by the way. All right, 91% of us say it's got to be 4, right? Because now if you brought a negative point charge near a neutral molecule, the electron cloud is going to be pushed away, right? Repelled. It's going to be repelled. So you get a polarization where the positive charge, the nucleus is here somewhere, the positive end of the dipole is closer than the negative end. Same couple of questions. What is the direction of the electric force? Well, let's do just the force. What's the direction of the electric force on the point charge due to the induced dipole? Now that it's been polarized in this way. Oh, split here. Force. The force, not the field. So let's do the field. Let's do the field first. You have a positive charge here, or a positive end here, a negative end here. So the field due to the dipole at this location should point in what direction? Should point in direction 7, right? The field due to the dipole points in direction 7. But now if you place a negative charge at that location, Q times E gives you the force. You're multiplying E by a negative charge. So the force is going to be in the opposite direction of the electric field. And so the force is direction 3. Force is direction 3, okay? So you get an attraction again. You still get an attraction even though you have a different point charge and a different polarization, okay? Does that make sense? Okay? I think maybe some people were thinking field instead of force here. Questions? So here's a question. A point charge is brought near a neutral molecule. Nothing else is nearby. Is it possible for a point charge and the neutral molecule to repel each other? Okay, 80% of us say no. The molecule can only polarize in a way that will attract the point charge. We pretty much exhausted the possibilities, right, with the previous 2 examples, right? So it looks like no matter what we do, we bring a positive charge near a neutral molecule, it polarizes in such a way that we get an attraction, right? Bring a negative point charge near a neutral molecule, it polarizes the opposite way, but we still get an attraction, okay? So let's just beat this to death here. Let's skip this one for now. You bring a positively charged tape near your hand. That thing is my hand. And And there are molecules in my hand, right? There are neutral molecules in my hand. But what's going to happen to those neutral molecules? Negative charges are going to be attracted by the positively charged tape. So what's going to happen to the tape? It's going to be attracted to my hand, right? If I had a negatively charged tape, what would be the best diagram for the molecules in my hand? 4, right? What kind of force would I get on the tape? Traction or repulsion? Traction again, okay? So this is the basic idea. It's induced dipoles, which is leading to this phenomenon we saw that both the U tape and the L tape, the lower and upper tape, whatever signs they were both attracted to neutral matter, both attracted to my hand, okay? So these interactions, I mean, we say, likes repel and opposites attract, but you got to be a little bit careful about attraction. In fact, let's just finish up with this question. You observe that a tape is attracted to a negatively charged plastic pen. What can you conclude about the tape? Can you say it's positively charged, negatively charged, neutral, positive or neutral, or any of those? Yeah, answer 4, right? It could be, well, let's see. It could be positive or neutral. Yeah, it could be positive or neutral, right? It could actually have an opposite charge, and that would be the cause of the attraction. Or it could be just the pen is causing induced dipoles in a neutral tape, and that could be causing the attraction, right? If it were repelling, we'd know that the tape had the same sign charge as the pen. Okay? Questions here? All right, I think we've got this. This is okay. We'll deal with more on issues of polarization next week.